right, we're live. And we are going to look at Formula 2 today. Yeah, I got to get started. Okay, cool. So here we go. Okay, so this is not going to be significantly different than Formula 1. It's just kind of a different way to think about slope. Actually, it might be the first way you ever learn to think about slope. Slope, as you might recall, I'll even write that down. Let's see, we'll write this down as, let's see, come on, pen. There we go. Recall that slope, the first time you ever heard the concept slope, you might have defined it as rise over, come on, pen, over run. So if you think about it as rise over run, then let's say we take a point, we'll call it point P. So we'll add point P to our graph here. And P is at some x coordinate. I won't use x though. I'll use a. So it has some a distance from the origin. And that means that the coordinates of point P are a, comma, and then whatever the function is. In this case, it's obviously a parabola. So there's point P. And then let me use a different color. Say up here at point Q. Let's say Q is the actual place I would like to know the slope at point Q. So Q is some distance further along. So let's call the distance between A and my new x coordinate, let's call that distance h. So this is then A plus h. So Q's coordinate is A plus h, comma, f of A plus h. All right.
With a person with a car with license plate DYN693, please come to the office.
Okay. So now, if we are looking for the slope at point Q, what you guys called in your physics class an instantaneous velocity, or if it was a velocity time graph, an instantaneous acceleration. I want the slope at that point. This was actually one of the key problems in physics that caused Sir Isaac Newton to actually sit down one pandemic summer in his aunt's barn and invent calculus. Physicists around the world were stuck on the idea of how do I figure out what the slope is when the rate of change is changing. In other words, what's the slope of a curve? There was no mathematics for that until Sir Isaac Newton came along and invented it. Now there were other people working on this problem from a different perspective. There was a German mathematician named Leibniz who was actually working on it just from a purely mathematical perspective. He wasn't really linking it to physics. Whereas Sir Isaac Newton, it was all about the physics. There has to be some sort of way for me to define the slope, the change of speed on a position time graph or the change of acceleration on a speed time graph when that change is curved. So this probably was more the way he thought about it than Formula 1. Okay, so we'll pick it up there after Oh Canada here. I'm just going to pause the video. Oops, I'm going to knock over the microphone. Sorry about that, guys. There we go, we're live again. Okay, so instead of thinking about joining points P and Q and making a secant line, which is how we found Formula 1, let's just think about the distances that we would call rise and run. So I'm going to use, let me use a different color here. I'll use green. So we already kind of defined this distance here as h, but h is of course what we would call the run. And we've already, and this distance here, assuming we make a triangle with a right angle in it, this would be my rise. And this can lead us to an alternate formula. Now again, the basic mechanics of what I'm doing is still the same as it was for Formula 1. Let me go back over to Desmos here and show you what I mean by that. Come on, Desmos. Desmos. There we go. So the basic mechanics are still the same. This is my Desmos version of your picture here. And that is, I'm taking point P and I'm moving it ever closer to Q. So what's happening is I'm shrinking the rise over run. But I don't know if you can tell this or not. As I get smaller and smaller, I'm actually not changing the proportions of the triangle. Rise over run is going to be the same no matter how small I make this triangle, because proportionately, assuming it is a curve with some regularity to it, I'm actually still going to have, say, a rise over run of 4 over 2 is the same as 2 over 1, for example. So proportionally, this thing's not really changing as I get smaller and smaller. So eventually, of course, I'll get to the point where one's on top of the other. So there we go. So there's what we're trying to accomplish. But we need a formula that describes it. And let's get back to our notes. And there we go. Okay, so everybody got the diagram? Okay, there is a little bit of a typo in the notes here. We'll fix it in a sec. An alternate formula for the slope of the tangent line for y equals f of x is obtained by labeling the coordinates of point P as, we'll say, a comma f of a, and point Q, a plus some distance that traditionally we call h, and then the y value where you run a plus h through the function, so that's f of a plus h. And then here's where the typo is. Can you change this? We're not talking, this is what we talked about in the first one, in Formula 1. Instead of x approaching something, as h approaches 0. Can you fix that? When we adapted the last lesson, we forgot to make those changes. So as h approaches 0, p approaches q, and the expression for the slope of the tangent becomes, well, let me start by, again, reminding you that we're looking at rise over run. Go back to the diagram, and you'll see, okay, well, what's rise? What is the green distance on this line? Well, it would be this coordinate minus this coordinate. So that will be f of a plus h minus f of a. And what will the run be? What's this? Well, we already kind of have we've defined it as h, but we can actually kind of tell that from the coordinates too. It's just a plus h minus a. So I'll write it out in full, a plus h minus a, right? How far is it along the horizontal? It's this spot minus this spot, which is this coordinate minus that coordinate. And that's going to lead me to this formula. F of a plus h minus f of a over a minus a, the a's cancel, h. So that would be the rise over run for this green triangle. But what do I want to do with the green triangle? Well, I want to make it infinitely small, right? I want to get point P and Q as close together as possible so that P basically becomes Q, and then I know the slope right at point Q. So what I'm going to do with that is, oops, I'm going to get the keyboard in the way. Get out of the way. I'm going to get the slope, come on, slope of a tangent at P when P approaches Q is the limit as h approaches 0. In other words, as this distance from here to here becomes infinitely small, and the 2 points become basically the same place. So Formula 2 is the limit as h approaches 0 of what is essentially the slope formula, but written as a rise over run. And now we can use this formula algebraically And that's what we'll do in our next couple of examples. So give you a sec to catch up to my notes there. Let me move that down a bit for you. There we go. Get it all on one page. Guys at home, I have a hard copy of these notes for you. Sorry that it didn't come in from the copier yesterday. You can just jot this down and then fill in the notes when I give them to you. Or you can, of course, go to your OneNote. I did send this to you in OneNote. Okay. All right, let's do some algebra now. These examples are going to look just like the ones that we did for Formula 1. But now we're using Formula 2. So find the slope of the tangent line when x is 3 of the curve f of x equals x squared plus 5x minus 1. Okay, so first things first, I'll start with the formula. It's the limit as h approaches 0 of f of a plus h minus f of a all over h. So this is my a value here, right here. So slope of the tangent when x is 3 is going to be the slope of the tangent when I rise over run from some point that's h away from 3. And then I'm just going to make h approach 0. So here's what that looks like. F of a plus h is actually going to be basically 3 plus h. I'll write h plus 3, right? You can add two things in any order you want. Minus f of 3 all over h. Okay, so now I'm going to actually plug that in. So that's the limit as h approaches 0 of, okay, so f of h plus 3. So I go to this function, and I plug h plus 3 in where the variable is. So instead of x squared, I have h plus 3 squared. Instead of 5 times x, I have 5 times h plus 3. And then there's still a minus 1. So this part here just took care of that. I still need to actually figure out what f of 3 is. You know, I might even do that kind of as sort of a scrap calculation on the side, because it'll probably be useful in part B to actually know the y coordinate when x is 3. So f of 3 is 3 squared plus 5 times 3 minus 1, which is 9 plus 15 minus 1. So 9 plus 15 minus 1. So I think that's 23. So f of 3, let me get a different color going here. So this part of the formula is going to go right here. So I have to now go minus 23. Oh, all over h. Okay, so now let's actually simplify this out. That's the limit as h approaches 0. I'm going to have to expand that. So h plus 3 squared is h squared plus 6h plus 9. 5 times h plus 3 is 5h plus 15. And minus 1 minus 23 is minus 24 all over h. Now, just like in Formula 1, the problem is the denominator here, right? If I plugged in a 0 for h, I end up dividing by 0, and I can't do that. If this is going to work properly, I should be able to see the constants in the numerator cancel. And then h will get canceled because I'll be able to factor it out of the numerator and divide it out of the denominator. And I can kind of see that coming. So this is the limit as h approaches 0 of h squared, and then I have 6 h's plus 5 h's, so that's plus 11 h's. And then notice I have 9 plus 15 is 24 minus 24. Isn't that nice? No more constant, which is good news because that's going to allow me to factor h out of the numerator and cancel it. H divided by h is 1. So I'm looking at the limit as h approaches 0 of h, and I just realized I forgot to factor my h off my 11. Can you fix that? Thank you. H plus 11. There we go. All right, No more denominator problems, so I can actually just plug in my limiting value. And remember, when I do that, it's not a limit anymore. It's just 0 plus 11. So there we go. The slope at the point that we're looking at is 11, according to this. So that's the A part of the question. The B part of the question was, can you give me the equation of the line, the tangent line? Well, I know that my slope is 11, and I have a point. Remember, my point had an x-coordinate of 3. And if you think back, I figured out that f of 3 was, what was f of 3? F of 3 was, it was 23, not 24, right? It was 23. Where was it? Yeah, there it is. 23 was f of 3. There we go. So I have the point 323. So let's make an equation. Y minus 23 equals m times x minus 3. And again, I'm just doing the same thing I did yesterday. I'm using the old point slope formula from grade 10. But most of the time, textbooks want that answer in standard form, so let's do that. Okay, we like our x to be positive, so move everything to the right-hand side. So 11x minus y, add 23 to negative 33, and I get minus 10 equals 0. All right, any questions on how I did that? It's similar to Formula 1, right? It's still got that same problem that we got to deal with the denominator somehow. Okay, now, just like Formula 1, we use this on functions that are more complicated than parabolas, right? This thing, at the end of the day, this thing was just a parabola. X squared plus 5x plus 1. In fact, why don't we take a second and maybe just Desmos this and make sure we did it right. So let's go to a Desmos page here. And come on Desmos. I'll just make a new page here. Graphing calculator. Come on Desmos. There we go. So let's say f of x is x squared, and what is it, plus 5x minus 1, right? And we'll shrink that in because we have to look way up at, what was it again? I think the y value was 23 or something. Yeah, so let's put that point on. Oops. Okay, just go home. Okay, there we go. There we go. And then just click over here. There we go. So let's put that point on there. P is equal to, and let's put the point 3 comma 23, right? Oops, that's not what I wanted. There we go. Yep. You're right. It's on the line, so we're good. And let's see if the equation we found looks like a tangent there. That's all I'm doing, just to check to see if I did this right. So the equation I got was 11x minus y minus 10, right? Minus y minus 10 equals 0. And that looks pretty good. Definitely looks like it is a tangent at this point. Okay, so I think we can be confident we got the right answer. Right, if you goofed up the algebra somehow, say you thought, I don't know, say you thought instead of 5 plus 6, you thought it was 6 minus 5, and instead of 11x, you got 1x. What would happen to you, of course, is you'd end up with, what kind of a tangent's that? It's not even touching the graph at the point it's supposed to, right? And then you'd realize, oh, okay, something's wrong with my algebra somewhere, right? Okay. Now, if there's anybody out there who actually, those of you going on, I think most of you are probably planning on going on to the AB calculus course next year, right? Once you're done your 40S pre-cal in semester 2, they do make you buy a graphing calculator, right? You're not allowed to use your phone and Desmos on the assessments for the AP schools tests and the AP exam. So you'll learn how to do this stuff on your graphing calculator. And I got to admit, it's actually a little harder because right here, you'd have to put this into y equals mx plus b form, for one thing. They don't allow you to do things like functions, and it's even kind of a drag on the graphing calculators to graph just a point, just so you can see where a point is on the line. But it's still doable. Everything I'm doing here can be done on a graphing calculator. So you don't really have to buy one until next year, but if anybody does happen to already have one, say older brother or sister finished high school and gave you their calculator or whatever, you could start bringing it in, and especially those of you who aren't in band, if you want to just have me spend some time teaching you how to use those calculators, I can. If it's something you're not going to touch until next year, it's not a big deal, right? You'll learn how to use it in AB Calc pretty well. But for this course, for our purposes, Desmos is fine. GeoGebra is fine too. GeoGebra does everything I'm doing, probably even more accurately. GeoGebra is probably more technical than Desmos. And there's a third option too. If you ever want to play with a program called Wolfram Alpha, Wolfram Alpha is a really good grapher. That might be the best of the bunch when it comes to the accuracy and the flexibility to be able to graph pretty much anything. It even gives you answers with complex numbers and stuff. Desmos doesn't do that. I don't know if GeoGebra does that either. I don't think so. So anyway, that's the technical stuff. Let's do another example. Like I said, they get tougher than parabolas. Let's do a rational one. Okay, so the formula is, let's write the formula again. The formula is the limit as h approaches 0 of f of a plus h minus f of a all over h. So now a here is -1, right? So that's my a. And this time they gave me the x and y coordinates, so I don't have to figure it out. This is f of a plus h right here. Or sorry, I mean this is just f of a. My bad, that's just f of a. So I would like to put a plus h in where this x is. So a plus h, really, is going to be -1 plus h. Why don't I just write that as h minus 1? So I want the limit as h approaches 0 of f of h minus 1, I'll write that down, minus f of -1 all over h. Okay, so that's the limit as h approaches 0 of, okay, so 1 over x plus 2 becomes 1 over h minus 1 plus 2, right? Replacing this x with h minus 1. I know what f of -1 is. F of -1 is right here. It's just -1. And there we go. Let's do algebra on that. First of all, let's collect like terms. And tidy up that minus and negative. Okay, so what tool is in your toolbox? Again, right now I can't plug 0 in for h. I'm going to be dividing by 0. So what would you grab from the toolbox here? I'd use my fraction skills, right? I'd use the property of 1 and times this thing by h plus 1 over h plus 1 so that I have a common denominator. So that's equal to the limit as h approaches 0 of 1 plus h plus 1 over 1 times h plus 1. I'm not going to bother writing 1 times. And instead of dividing by h, why don't I just times by 1 over h? And let's see, what's going wrong here? Something's wrong here. Oh, hang on, you know what? I actually do have this wrong. Sorry about that. That's not right. Oh, I got to fix this. Sorry about that. Okay, f of -1 is, go away, is 1 over, I think I've got that wrong. Yes, I do. It's -1 plus 2. Sorry about that. Oh, go away. -1 plus 2. Sorry about that. I had the wrong number there. It's not -1, or it's not minus -1, it's minus +1. Guess I shouldn't have skipped that step. That was a bad idea. So this is -1, not +1. See that? I kind of knew things weren't working out. My algebra wasn't going right. I did this part right. I am timesing by h plus 1 over h plus 1. But instead of it being a plus, it is 1. I guess I have to fix this too. It is 1, this one here, minus 1 times h plus 1. So it's actually 1 minus h plus 1. Which is the limit as h approaches 0 of 1 minus h minus 1, which is -h, and that allows me to cancel these h's, because now they are factors, and that leaves me with the limit as h approaches 0 of -1 over h plus 1. Sorry about that. See, you lose track of one negative and the whole thing's wrong. All right. What happens when h becomes 0 now? No problem. So let's just plug it in. So it's not a limit anymore. I'm actually using my limiting value, and I'm getting a slope of -1. So that's the A answer. The slope at the point is -1. And the B answer, we are going to do, let's see, so the slope is -1, and the point that I'm doing a slope from was -1, -1. That's a lot of -1s. So point slope formula says y minus -1 equals m times x minus -1, which is going to be x plus y, and then -1 move to the other side, so plus 2 equals 0. All right. Give you a sec to catch up to me. And let's see, what kind of a graph is 1 over x again? Can you picture it in your head? All right, it's the one with the two arms, right? Okay, so somewhere it's a curve, and we want the slope of it at x is -1. So let's see if we can see what that looks like. Okay, so let's just adapt the graph that we had before here. Sorry about that. Okay, so let's see. Let's just go back to home. We'll get these out of the way. Okay, I'll just use y because I've already used f of x. Y equals 1 over x plus 2. There we go, the two arms. And we want, I'll call this one point Q because I already called the other one point P. So point Q is -1, comma, -1. And that's not on the curve, is it? Find the slope of the tangent on the curve 1 over x plus 2. That point's not on that curve. Interesting. You know what? I think we've got a mistake in the notes here. -1. Here, I'm going to call this. Yeah, -1 doesn't make. That should be a +1. Can you go back and fix that? That's why I goofed it up. Okay, go back to the notes. My bad. I didn't notice that mistake in the notes. This should be a +1 up here. Can you fix that, guys? That should be a positive. There we go. Yeah, because we actually found that it was positive when we did the actual math. Right. Okay, there we go. All right, now let's graph. Now that we've got that sorted out, so there's the point. So according to our math, x plus y plus 2 equals 0 should be a tangent at that point. Let's see if it is. X plus y plus 2 equals 0. Right, so that means, okay, good eye. So that actually changes the equation a little bit, doesn't it? Because this is now, thanks for noticing that, that's a plus. So that makes this a minus, right? And that makes this a +2 on this side. So when it moves over, it becomes a -1, right? Somebody double check my mental math on that. But I think, oops, there we go. I think that's right. That look good? All right, let's see. Does this work? So x plus y. Oh, it's just +0. Yeah, you're right. Let's go back. I have to fix it again. Oh yeah, because these two ones just cancel. So there we go. So that's just x plus y equals 0. And there it is. Graphically, yep, looks like a tangent to me. There we go. Desmos helped us find mistakes in the actual question. All right, I only have a couple minutes. Let's see if we can get through one more. All right, so we've done a rational one. We did a parabola. Let's do a radical one. Okay, first of all, let's do a double check and make sure the point's right. If x is 6, 6 minus 2 is 4, the square root of 4 is 2. Yep, that one works this time. All right, so let's use the formula. So the formula is the slope is the limit as h approaches 0 of f of a plus h minus f of a all over h. And we are going to this time have a is 6 and f of a is 2. So that's going to equal the limit as h approaches 0. So a plus h is 2 plus h. I'll use h plus 2. So I'm replacing this x with h plus 2. Or sorry, oh, no, what am I saying? It's not 2, it's 6. Sorry, that's better. Right, a is 6. There it is. I underlined it and I said it wrong. And then, okay, and then minus f of a. So f of a is just 2, so minus 2, all over h. Okay, there we go. Let's tidy that up before we do anything else. So that's the limit as h approaches 0 of 6 minus 2 is 4, so that's the square root of x plus 4 minus 2 all over h. Oh, good. Can I square root that 4? No, that is a binomial. I can't just distribute a power through a binomial, right? Okay. People who would look at this and go, oh, don't write this down. The square root of h plus 4 is just the square root of h, come on, pen, plus 2. That's wrong. For the same reason, actually, if you want to think about it, it's the same reason why h plus 2 squared does not equal h squared plus 4. And if there's people going, doesn't it? You should know that you're foiling here, right? You can't distribute a power through a binomial or a trinomial or anything that's more than one term. And the same thing is true here because logically, isn't this a power also? Isn't the square root the power of a half? So it's the same rule. The same reason why this is wrong would be why this is wrong. So that makes our life harder. We can't just square root that 4 and make it a 2 and get on with our merry lives. What do? We times by 1. But this time our 1 looks like this. Right? So we rationalize the numerator. And that's going to give us the limit as h approaches 0 of h plus 4, negative 2 times 2 is minus 4. And there's no point in multiplying out this numerator because, as you can see, those h's are going to cancel if I leave them as factors. Because 4 minus 4 is nothing. And then I'm going to have the limit as h approaches 0 of h over h, which is just 1. Those h's cancel. So I have the limit as h approaches 0 of 1 over, and this looks just as complicated as when I started, but it has an important improvement over the one I started with. H equals 0 doesn't make me divide by 0 anymore, so I can just plug it on in. It's 1 over the square root of 0 plus 4 plus 2, and so that is 1 over 2 plus 2, which is a quarter. All right, let's get to an equation now. So the point was 6,2, right? Or is it 6,3? No, it was 6,2. The slope is a quarter. So I am looking at y minus 2 equals a quarter times x minus 6. Okay, if I want standard form, the easiest way to do that is to just multiply both sides of the equation by 4 and then move everything to the right. X minus 4y plus 2 equals 0. Okay, and once again, I kind of want to see, using my grapher, what does this look like? So let's see. Give people a sec to catch up, and we got like 1 minute. Can I graph this function on Desmos in 1 minute? Minute to win at Desmos. Come on, Desmos. Oh, no, it's being slow. Okay, let me just get a new page here. New page. Oh, hang on. New page, forget it. I'll just close those. Okay, so the original function was y equals the square root of x minus 2. And we are graphing the line x minus 4y plus 2 equals 0. And as you can see, it's looks like a tangent right at 6,2 where it's supposed to be. Ta-da. We did it. Okay, check the blog. I put an assignment up, which is basically just going to be filling in the gaps of yesterday's assignment. Band guys, away you go. Tomorrow we're just going to have some work time. I'm going to let you guys have a work period on the assignment I put on the blog today. And if anybody's finished it, you can just do some more stuff from the back of the booklet. Okay, so we slow down, let you have a chance to work at this stuff tomorrow. Guess I can shut down my video. Let's see what happens. Looks good today.